Hi, welcome back. We're going to start our discussion on topic 7b, which discusses, so we just did 7a, which talked about why we need a new theory. Classical mechanics doesn't work based on the wave properties of particles. So now we're going to talk about what the new theory tells us and how we can understand the dynamics of microscopic systems with it. So once again, I will share the camera. Think. Okay, should be able to see that. So we're going to talk about the dynamics of microscopic systems. So the key idea is all dynamical properties of a system are contained in the wave function. So we're going to take this concept of a wave nature and find a way to calculate a wave function for any system. And then we'll know that anything we can know will be contained in there. And so we're going to do that by solving Schrodinger's equation. So the wave function that we're going to solve for is a mathematical function that contains all the information about the state of a system. So in classical mechanics, we could know everything. We could know where a particle is. We could know how fast it's going, but we can't know all of that any longer now that we know that particles have a wave nature. But we can know a lot of things, and everything we can know, we have to obtain this wave function to figure out. So Schrodinger's equation is a differential equation. So it's given here at the bottom of the screen. So it says negative h bar squared. H bar is h over 2 pi. Just ends up that Planck's constant divided by 2 pi is a pretty common thing to run into. So it's given its own name. It's called h bar. So negative h bar squared over 2 times the mass times the second derivative of the function with respect to x plus the potential energy function times the function should be equal to some constant times the function. So this is the equation you solve if you say you're solving the quantum mechanical system. So we need to know about each of these terms, and we'll use this equation a lot, so you'll get familiar with it. First thing you have to think about is what's a differential equation. Sounds like you should have had a course on differential equations in order to take this class, but that's not really true. A differential equation, which is in this toolkit on page 324, is really just an equation that's a relationship between a derivative or a second derivative and the function itself. So notice Schrodinger's equation is a relationship between the second derivative and the function itself. So it's a ordinary differential equation if we're in one dimension, because it's only a function of one variable. And so read this carefully, but the important thing is what we're going to do with differential equations to solve Schrödinger equation is really just calculus that you'll understand. So saying something is a relationship between a derivative and the function really is something that's part of Calc 2. So read this just to get a little better understanding of what's going on, but know that the math is not beyond the scope of Calc 2. So first thing, it tells you that h bar is h over 2 pi and gives you the number for that. So that's also in your table. When we look at Schrodinger's equation and pull it apart, this first term, the negative h bar squared over 2m second derivative That's considered the part of Schrödinger's equation that gives you the kinetic energy. The second term, the V of x, that's usually the symbol given for potential energy. So this says potential energy is a function of x. So we have a particle that can move in one dimension, and maybe at some point it interacts with another charged particle, something like that. So we need to know the functional dependence of the potential energy. That's multiplied by the function. So here we took a derivative, here we're multiplying. And when you solve Schrödinger equation, you're looking for functions where you get back the function when you do everything on the left-hand side, just times a constant. This is usually abbreviated. H bar is all of this operation stuff. So it's the operations taking the second derivative and multiplying by Vx. So in this case, the Hamiltonian would be equal to so it's all of the operations. So looking at this, you're taking the second derivative, multiplying it by some stuff, and then you're multiplying the wave function. So this just abbreviates that. And that H, called the Hamiltonian operator, is the operator that will tell us the energy. So this E right here is the total energy of a system. So what we want to think about is how to solve this equation. So sometimes it'll be easy to solve, sometimes it's impossible to solve. We'll see that you can solve it exactly for the hydrogen atom, but for no other chemical system. So as we go through this, we want to think about why it's such a challenging equation for atoms and molecules. This at the bottom just gives you an idea of some of the wave functions. You don't have to worry too much about that because we're going to go right into looking at some of the wave functions. So once you see them, you'll realize what kinds of functions are equal to their second derivative times constants. I think I do this. Yeah, so in this justification, it's looking at the solutions for a freely moving particle. And if we look at them, let's just look at how you'd actually solve that system. Okay, so they tell us that one of the solutions is sine k of x, so some constant times x. We want to just confirm that and determine what the value of k should be. So when you say it's a freely moving particle, so this is the justification, justification 7b.1 essentially. So when you think about what it means for a particle to be freely moving, it means it moves in the x direction, but it never runs in and interacts with anything. Doesn't see any other particles, it doesn't see any other forces. So that means the potential energy in the x dimension will be 0. That means when we look at our Schrödinger equation, when we look at our Schrödinger's equation, which is right here, this second term will be 0 because potential energy is 0. So all we'll have is the kinetic energy part. So the kinetic energy part is the negative h bar squared over 2 times the mass of whatever the particle is, times the second derivative has to equal the energy times the function. So if we say the function, one of the possible solutions is the sine function, you should remember from calculus that you take the derivative of sine, you get cosine, then you take another derivative, so the second derivative of cosine gives you negative sine. So the second derivative of sine with respect to x gives you back the function sine times a bunch of constants. So let's just go through our derivatives. So this derivative of psi with respect to x, our proposed wave function, is the derivative of sine kx with respect to x. So you get k cosine kx. Now we need the second derivative, so I'm going to take the derivative of the first derivative, and what I end up with is negative. The derivative of cosine is minus sine, and you get another k, so you get negative k squared sine kx. So for the left-hand side, if I group all those constants together, I don't have my red pen, you will see that you have psi times negative h bar squared over 2m times negative k squared. On the right-hand side, you need to have energy times the function. So this energy has to be equal to all of these constants. So this energy is equal to all of these constants. So negative times negative makes it positive. H bar squared, k squared over 2m. And so the energy of a free particle is h bar squared, k squared over 2m. And so you can solve for k in terms of the energy, and you end up with square root of 2 times mass times the energy divided by h bar is what the value of k has to be. So that's what you would put in for this k. It's not an unknown parameter. It's a parameter based on the mass, the energy, and Planck's constant. So you get a wave function. What meaning could a wave function have? So the first thing you want to think about a wave function is Born's interpretation. So Max Born was part of the quantum team. Many famous names: Heisenberg, Schrodinger, Einstein, Born, Bohr, all working on this Planck at the same time. And Bohr looked at that wave function and said, well, there's not much meaning in it. It can be negative, it can be positive, it can even be complex, so it can have I in it. And so what could that possibly mean? And he came up with the idea that the probability of finding a particle in a small region of space of some small volume, delta V, is proportional to the wave function squared times that volume. And so that's the important meaning of the wave function when you think about it directly. It has other things that it can tell us, but in terms of itself, the biggest physical interpretation is that the square of that function tells you the probability of where you're going to find a particle. So if psi squared is large, there's a high probability of finding a particle there. And if it's small, there's a very small chance. So when we look at this wave function up here, for example, at any node, the wave function squared is 0, so 0 probability. As it goes to infinity, gets smaller and smaller, so very unlikely to find the particle here. You have these high points here where the wave function squared is large, so you'd have a large probability. So let's just do self-test down below. So in this worked example, it's telling us that the wave function for a hydrogen atom, which we're going to look at the solutions to later, is equal to e to the minus r over a0, where a0 is just a constant. And r is the distance of the electron from the nucleus. So it asks us to calculate the relative probabilities of finding the electron within a very small volume located at the nucleus versus at a distance a0. So what we want to do is take the ratio of psi squared at the nucleus to psi squared at r equals a0. So at r equals 0, e to the minus 2 r over a0, because that's the wave function squared, is going to just be equal to 1, because e to the minus 0, if r is 0, is equal to 1. So at the nucleus, it's 1. What's the probability of finding it at a0? So psi squared equals e to the minus 2 r a0, because e to the minus r over a0 times e to the minus r over a0 is equal to e to the minus 2r over a0. So if you take the location where r equals a0, then the wave function squared is equal to e to the minus 2. So if you take the ratio of 1, which is at the nucleus, over e to the minus 2, you get 7.4. So it's almost 7.5 times more likely to find the electron at the nucleus than it would be to find it at a distance a0. So they want us to redo that problem, but now do it for a helium cation. So a helium cation has a wave function that's the same functional form, but it's e to the minus, let's see, I have it right here. It's e to the minus 2r. So 2 takes into account if you have a helium nucleus, the charge on the nucleus is 2 instead of 1. So you end up with a 2 in the wave function. So they want us to get that same ratio. So at the nucleus, the product of these two still, because there's an r in there, ends up being e to the minus 0. So it's 1. When we're at a0, this times this ends up being e to the minus 4r over a0. So at the place where r equals a0, this is e to the minus 4. So the wave function squared at a0 is e to the minus 4. So the relative probability is just what we calculated in a divided by b. So 1 divided by e to the minus 4, and you end up with 55. So that's a larger number than the 7.4 for hydrogen, where Z just equals 1. So as the charge on the nucleus gets bigger, we know that it holds the electrons tighter. So there's a greater probability ratio that the electron is at the nucleus when you have a helium plus than when you had a hydrogen plus. So because of this interpretation that lopsided. Yeah, that looks readable. So the important thing is if we're going to interpret the wave function squared to have properties of telling us the probability where a particle is, then that function has to have some mathematical properties. The first is it has to have a single value at every x. Otherwise, you'd have more than one probability at each x value, and that's not possible. It also can't be infinite over a finite region of space, because if it was, then you'd have an infinite probability of finding the particle someplace, and that makes no sense. So the boundary conditions we're going to find are the conditions of the wave function at different locations in space. The wave function is continuous everywhere. It has a continuous slope everywhere. Those are things that are boundary conditions. So these locations, it can't have places where it's discontinuous, and it also can't have an undefined slope. So when you look at this picture, that helps you think about those. So these wave functions are all unacceptable, because in A, you have 3 different values for the wave function at the same point. So you'd have 3 different probabilities, which makes no sense. In B, it goes to infinity over a finite region of space, so you'd have an infinite probability. In C, the wave function has 2 different values at the same location. That doesn't make sense. It has to be continuous. And in D, the slope also has to be continuous, and that function is not true. So that's just a graphical to show you what they're talking about in terms of what properties the function has to have in order to be a physical solution of Schrödinger's equation. So when Schrödinger's equation is solved subject to boundary conditions, that the solutions must satisfy, it's found that the energy of a system is quantized. And we're going to see that firsthand when we solve the particle in a box. So there's more information in the wave function than just the probability of where a particle is. And so we'll see later that you can figure out things like momentum, all sorts of things can be extracted, angular momentum, by using operators. So we'll learn more about the math of how you extract other information from the wave function. One thing you can think about is that if the function is really wavy, it's going to have a large second derivative. And in that Hamiltonian, it's the first term that has the second derivative that's equal to the kinetic energy. So that means if the function is really oscillating, it has a high kinetic energy. So that'll just be one of the things that we can learn from the shape of the wave function. And we'll think about more as we go through the different types of energy in atoms and molecules. Okay, so an important concept, and this is something that's almost as famous as E equals mc squared. Heisenberg's uncertainty principle is the subject of many jokes in science, of course. And essentially you want to think, because of that wave nature of a particle, you've lost some information. And the Heisenberg's uncertainty principle says it's impossible to specify simultaneously with arbitrary precision both the momentum and the position of a particle. So if you put that into an equation, it's here on this page, that the uncertainty in the momentum times the uncertainty in the position is always going to be greater than or equal to 1/2 h bar. So that's Heisenberg's uncertainty principle. The very best you could get is equal to, but within the equipment you're using to measure these things, you're always going to be greater than that. So this is the theoretical limit. So you can think about it by looking at these two diagrams in terms of what we already know. So if we have de Broglie's wavelength, if you know the wavelength, you know momentum, but that makes it so that you lose all the probability. Just wait. Okay, so here we're looking at the wave function squared. Here we're looking at the wave function, just so we can see them interfering with each other. So if you add together a whole bunch of sine functions, you're going to converge and you're going to get this picture here, where essentially if you add together an infinite number of sine functions, so remember our wave function is sine kx. So if you added together tons and tons of these to infinity with different k values, their interference pattern would allow you to get a wave function that's single peaked. That would mean an infinite sum of these, each of which had a different momentum, gives you an exact location. But as soon as you had to add these all together, because energy, or k, is a function of energy, which means it's a function of momentum, if you had to add tons of these together with different e's or different momentums, that means when you know exactly where it is, you know nothing about how fast it's going. So in vice versa, if you have only one sine function where you know exactly the energy, then the wave is spread out to infinity and you know nothing about where it is. So those two diagrams should help you think a little bit about the properties of a sine function and how they can help you visualize the Heisenberg's uncertainty principle. So these are problems similar to what you would have done in Chem 107, really. So we'll just look at this problem 7b.2. They want us to calculate the minimum uncertainty in momentum if we know something about the uncertainty in position. So what they tell us about position is, so estimate the minimum uncertainty. The minimum uncertainty in the speed of an electron in a hydrogen atom, and we're going to assume that the diameter of that atom is 100 picometers. So they're giving you the hint that if that's the diameter, the electron can be found anywhere in there. So we'll assume that that 100 picometer diameter is the uncertainty in the position. So if I rearrange this to get the uncertainty in momentum, the first thing we want to think about is if we replace the inequality with the equal sign, that's the very best you can do. So that's the minimum uncertainty. So it'd be h bar over 2 times delta x. So I just use the value of Planck's constant. So I put Planck's constant over 2 pi, gives you Planck's constant over 4 pi with this 2. And then putting in the value of the diameter as the uncertainty in x, it'd be 100 times 10 to the minus 12 meters. I solve for the uncertainty of momentum, and then by putting in the mass, so assuming that the mass of the electron is known and the uncertainty in momentum is really a result of the uncertainty in the velocity, because momentum is mass times velocity, you can solve for the uncertainty in the velocity, which would be the minimum because it's equal sign, is 5.79 times 10 to the 5th meters per second. And I think that is all for this on the dynamics. Next thing we'll do is we'll solve 3 different problems of motion. We'll solve translation, rotation, and vibration, and you'll get a much better idea about some of these concepts. They're easier sometimes to see with concrete solutions versus in the abstract of this focus.